some unusual pattern in this picture. Is it smooth? It's not smooth. What is it like? It's a typical, the way we call it as a jagged curve. There's a word so-called jagged. If you haven't such a word before, just look it up. Very jagged. Smooth curve is something like this. There's not much change if you narrow down the local neighborhood of this time series. But this one is more like that. Very choppy. Lots of ups and downs. What does that mean? The curve is not something like this, but more like this one. Means what? It's very uncertain. That's what we mean. So this kind of smooth curve, there's a little uncertainty, so it's more like a certain. But jagged curves like this one presented there is very uncertain. From the potential investor's point of view, which one's better? Smooth one or jagged one? Why? Exactly. If it's a jagged one, you don't know where to sell and when to buy. So presumably, the best time to buy these stocks should be like this point. So same stock, but you can buy at the lower price. But then you might want to wait a little bit and then just dump everything in the price reaches its local peak. But nobody tell you in advance that when this time peak is gonna come. Could be like next April or next, I don't know, August or maybe sometime in the winter. Totally unknown to those investors in advance, so they have to guess. They have to try to predict when will be those optimal time point to dump everything that you have in the market so then you can maximize your so-called profit or return. So return is nothing but the price difference. So if you buy those stocks at this time point and that's how much you pay, but then if you dump everything into the market at this time, that's the price that you receive. So that's your revenue, and this, as much as this you pay, that's your basically cost. And difference between revenue and cost, what we define as return or profits. You want to maximize that. So how do you predict this one? This jagged and rather uncertain time series process, if you want to forecast or predict, how do you do it? Toss a coin. Head you buy and tail you sell. Or roll a die. If you come up with a 1, you wait one more day. If you come up with 2, you wait 2 more days. Something like that. How do you predict? Well, you at least see the point at why you want to predict it. Because you want to make the most money out of it. So you want to know in advance when this time point will be. So you buy the same share of stocks as sometime before, like here. So buy them at a relatively lower price. You want to wait a little bit more when the market turns a little bit higher, and then you sell them so that you can maximize your profits. But in order to guess when those specific time that you need to dump everything into the market, you need to predict it, forecast. But how do you do it? You forecast using so-called models. So it's nothing but mathematical equations, formulas. So some smart people come up with, and then you just run those models so that those models can crank out some numbers. What should be those specific, time that you can utilize to maximize your potential profits? One of those well-known models that reasonably well predicted stock prices is a random walk models. You don't have to know this one. Just telling you know, letting you know in case you're interested in. So name is a random walk model. Who was the first person who invented this one? I don't know. This one dates back at least to the 18th century. Some famous mathematicians from maybe France or Germany might have come up with this idea. As the name suggested quite correctly, everything is random, but it's in some sense random walking. So standing at specific time point, there are two possibilities. The price might go up or go down, and chances of each outcome is exactly the same, 50% chance. So starting today, there's a 50% chance that the specific company's stock price will turn up, and exactly the same 50% chance that the price will turn down. In that sense, it's completely random. So that's where the name random comes from. You walk, but the chances that you will turn left exactly the same as that chances that you will turn right. So it's just like walking in some random fashion. And that's one of the models, tons of different models that people have invented so far, and use them in practice to try to forecast these prices better. So statistics, given this bunch of collection of numbers, index is just the numbers. These are numbers. Index one day might be a 506, or next day could be a 600. This is just the path of the time series plot. Given those collection of bunch of different numbers, you first want to understand what's going on, and then come up with some systematic relationship between time and those collection of numbers, so-called models, something like this, so you can use in practice, so you can get the most out of it. So that's statistics. Another example of what statistics can do to you in everyday life could be this one. So today just basically deal with a bunch of different pictures, nothing more. No deep theory or no deep modeling, or since it's a first class meeting. So this one is again two-dimensional, but the numbers are quite different. Down here, you read it as a per capita GDP. So PP means per capita. What's per capita? Per person. Yeah, what's GDP? Economy. Yeah. So total income. So strictly speaking, that's a gross domestic product. There are zillions of different businesses and individuals who produce or generate certain services and goods during specific time period, typically 1 year. You add them all up. So including all those individual companies and businesses or corporations, how much value of those the goods and services were produced and consumed during a certain specific time period. In aggregate sense, that's what's called the GDP. National income, basically. And then you divide it by the size of population. It becomes a per capita GDP, which is a typical measure of when do these people use these measures or indexes. So unit is some currency divided by size of population, which means the per person. So here in the US dollar term, real term, because you have to deflate it. So that's why the numbers are rather big. So 40,000. The data was collected back in 2000. This is a UN data set. So the nominal sense, these numbers might look small, but actually it's not. You have to take into account the fact that this one was collected more than 14 years back, but then these numbers are real. You have to deflate it using those price indexes. So salary that you get now is just a nominal income, but you have to adjust it depending how high those prices are. So once you do that adjustment, number gets deflated, looks small. But by actual, the meaning of that number is not small at all. It's actually a quite big number. So that's a per capita on the horizon. Down on the up in the vertical one, we have a fertility. What's fertility? I feel like more is an English class or something. What's fertility? What baby? Well, that's called a pregnant. What's fertility rate? It has to do something to do with babies, but in what sense? Number of babies, newborn babies per household. But you look at these numbers, it's between 1 and 8. You're saying that 1 to 8 babies per couple. That's per 1,000 female. So number of newborn babies per 1,000 females between the age of 15 and 55, because they at least have to be able to have babies. But then how come these numbers can be non-integer? These numbers all over the place between 1 and 8. Could be 4, but could be like a 4.4 or 4.6. If it's a number of babies, how is that possible? How do you define 4.5 babies? I don't know how to define it. You just have 5 babies and the fifth one is just to chop it off and then count it as like a 40%. The numbers can be non-integer because the size of population is not guaranteed to be 1,000. Could be like a 50,000. In that case, you have to divide the total number of babies by number 50. But then there's no guarantee that the division will produce the still integers. Certainly will be more likely to be non-integers. It just means how fast those population is growing. The higher the fertility rate is, that means that the population is growing fast. So having fertility rate of 8 certainly means that this economy, the nation is growing a lot faster than any other nations that might correspond to these lower numbers, around like 1 or 2. These are national data. So little dot represent one nation, UN member. If you count all these little dots, there will be like a 200. Where would South Korea will be? Roughly speaking. Where's the South Korea? So in terms of per capita income is just under 30,000, is it? So somewhere here. But in terms of fertility, it's one of the lowest. So it should be around in this vicinity. Very low fertility, but a rather high per capita income. So countries like the US, UK, Japan, and Germany are all located in this side because those are the group of nations and economies characterized by high income growth but low fertilities. But other less developed countries might be more like along this side. Countries in Africa or southern hemisphere, some other less developed economies, the per capita income is relatively low, but their population tend to grow fast. So given this second data plot, what can you tell other people who have never seen this picture like this? What are some of those important features, characteristics of this data? So what's your first impression if you see this one? Other than there are lots of dots. And why possibly the economics majors might be interested in pictures like this? You don't say anything. What's the first impression? What's the obvious thing if you look at this one? Don't tell me you don't. I know that you do. It's just you don't know how to put it out. What's your very first thought if you see this picture? Inverse relationship, which means that the richer the country become, the fewer babies are born. How do you know it? Because the relationship is negative. Something like that, rather than this. It's inverse relationship. As X grows, Y tends to go down. Why is it significant meaning? How come this outcome is significant? Is that the kind of thing that you expect or you don't expect? As the income level of certain economy goes up, people in that economy tend to have fewer babies. Is it intuitive or counterintuitive? Counterintuitive, yeah, obviously. I mean, the more income means you have, the more time and, resources they can use to have more babies if you want. But how come the direction is the opposite? As your income level rises, as more and more resources become available to you, people tend to, be less interested in having babies. Why? What could be one explanation? As someone well, actually the first guy, who was able to answer this question in a very systematic way using some economic models, won the Nobel Prize. I think, and since that guy won the prize, and many of other, it's mostly students, followed that line of research to complete the small discipline in economics these days, so-called family economics. So one way that most economists, especially in the micro side, rationalize the rather counterintuitive inverse relationship between this income and price is so-called the price effect of those having babies. But that's way more into so-called the microeconomics, so it's not certainly within the scope of this class. But the important thing is having data like this one, you want to summarize in such a way that there seems rather counterintuitive negative relation between this income level and number of babies born. And then you want to model it and explain better how come this rather unusual phenomena can be observed in actual data sets. Those are the type of things that economics people want to do using so-called data or numbers. Okay. Anything so far? Any comments or questions or thoughts that you might want to add? Is it boring? Not boring? Is it exciting? Certainly not exciting. What is it? Is it tough? Of course not tough, it's just the pictures. We haven't even introduced the formulas or equations or models, and how can it be tough? It's just the two pictures. One picture, the relation between time and stock price index. The main conclusion we try to make in this class is it's very choppy, uncertain, hard to predict. So we need some kind of a modeling approach so that we can come up with some reasonable, accurate forecast of this series. Second example, relation between how fast population grows and how much money the economy makes. And there seems to be rather counterintuitive, negative relation between the two. And then economists have worked so far in order to explain how come this nonsense actually observed in the real data sets. So the price effect and family economics. And many other examples, many more examples. And other example that we introduced it at the end of this first lecture note is environmental economics. So you just talk about this one briefly. We don't actually jump into the actual material today, just some introduction of what's the purpose of studying so-called statistics, especially from the future economist's point of view. There's a famous model called the environmental Kuznets curve. You might have heard of this name, Kuznets. It's a guy's name. He's a Russian-American, Ukrainian-American to be more specific. Past Nobel Prize winner, was a famous professor in economics at Harvard. You know what Harvard University is? One of the best ones. He invented the model that this Simon Kuznets invented was actually Kuznets curve, not environmental Kuznets curve. But two other economists who work at Princeton University dubbed this, the second version of this Kuznets curve as environmental Kuznets curve, basically describing the relation between amount of income that people make and the amount of pollution coming out. You know what pollution is? Air pollution, water pollution, all those, the chemicals generated out of factories, or when you burn fossil fuel, some poisonous gas emits, and then they can measure the amount of pollution, and that's what's being on this y-axis. So the theory predicts that the relation between this amount of income and the amount of pollution, the air pollution in this particular context, is inverted U. So U curve is a quadratic curve, is typically this one. But if you put it upside down, you get something like that. So that's just an untested model, economic theory. There's an inverted U relation between the amount of income and amount of air pollution. Why does this inverted U characteristic make some sense? How do you interpret it? What's the message that this the environmental Kuznets curve try to tell you? Other than it's very smooth this time. So as the economy gets the richer in the beginning, more pollution comes out. Why? So I'm talking about this left-hand side. So forget about the second half, only focus on this first half. Yes, X goes up, obviously Y increases, so the relationship is first positive. Why could that be? Well, think about the South Korean economy back in the 60s and 70s. You have to, produce more outcomes. You have to build more factories. You have to burn more fossil fuels to run the factories, to jack up the production. So amount of pollution is supposed to come out a lot more. So as the income level rises, there's a stronger need for producing more stuff. So you need more resources. So more fossil fuel is coming out, basically burning them. So as X goes up, Y also increases. But there's a turning point, obviously, which is this peak. We don't know where exactly this peak point is, but there is somewhere. And then if you pass that point, if the nation or economy gets richer and richer, relationship is turned around. Actually, the amount of air pollution comes down. Why? So if the left-hand side of this picture makes sense, there might be some other way to explain, rationalize this rather counterintuitive behavior on the right. But why? If the South Korean economy back in the 70s and 80s can explain this intuitive behavior, now look at the South Korean economy now. That's basically this. More and more people talk about the quality of air, quality of water, quality of land, quality of many other stuff. So they, increase the budget or pour more resources into those quality of environment so that people can enjoy those better qualities rather than less. So bottom line is that at the beginning of the developing certain economy, people cannot afford to think about environment. Making their living is much more, important top priority. But once the income level reaches or goes beyond certain minimum level, now they can afford to think about other factors that can affect the quality of their lives, and one of them are possibly this environment. So economies like China or India, if I have to characterize them, probably on the left-hand side now, they're not quite well developed at this point, but they're moving on. So they don't really care about those quality of environment at that point. So the pollution, more and more pollution gets immediate. But then once they reach certain turning point, so those countries like US or UK or some other European nations might be on this right-hand side. Once you pass that stage, the income gets higher and higher. People then can afford to think about those other factors, not directly related to those developing economy, but still important to their lives. So a lot of meanings actually can be captured under this one simple curve. But that's just a theory, models, suggestions, cooked up by some economists. You have to test it using the data set. So that's what the statisticians are trying to do, using so-called statistic models and way to analyze these data sets. And that's what's coming after. So after you're actually getting those data, amount of air pollution and then amount of national income, you want to first estimate it. What's the true hidden underlying relationship between this quantity of air pollution and the level of national income? You first fit the model. So these are the data, not models. And then try to come up with some meaningful conclusions. The testings about those unproven and untested hypotheses cooked up by some of those economists in the end. 3 examples. The first one, the stock price example. Second example, the relation between the fertility rate and national income level. Third one is the environmental Kuznets curve. All can be used as like a little motivation of why people want to bother to learn so-called statistical science, because you want to learn those essential skills that you're going to need to analyze, decode, or handle those so-called data sets. Nothing but a bunch of numbers that you're having. Not just random numbers, numbers based on some meaningful relationship, economic relationship. So in order to conduct such exciting or rather interesting projects in the future, you first need to know those nuts and bolts of those statistical science. Taking mean is some of the simplest way to summarize the data characteristics, but there are many more, and we're going to learn them one by one as this class moves on throughout the semester. So when we come back next time, which is Tuesday, 10:30, not 9, we're going to start from page 6 of the first lecture notes. Definition, starting with the definition of population and sample. So today is just basically the informal introduction of what this statistical science is basically about. If you have any questions, you can ask me now, because I have to teach the same class that starts at 10:30. In case you didn't come to class for some reason, say that you got up late because you have a hangover on Monday morning, there's no restriction on your side that coming to the second class, which starts at 10:30 right here, I get to teach the second section, section 2 of this exact the same introduction to economic statistics. But for those quizzes and exams, you should be in the right section. So if there are no quizzes and no exams, it's just lecture purposes, for some reason you couldn't come to this first class, then you're more than welcome to come to the second one and then attend it, because I'm covering the exact same stuff for this one and the one that comes next. All right. Thank you. See you tomorrow.